Good evening one and all. I welcome you all to Ganesh IAS Academy. In today's session, we'll be seeing science and technology based current affairs from the date August 7th to August 13th, 2023. Let us get into the news articles one by one. The first news for the day is LK99. What is this LK99? Why is it in news? We have to know. A group of South Korean scientists have recently claimed discovery of a material that they named LK99. So what kind of material it is? It is a superconductor at room temperature and pressure. So they are claiming that this LK99 can be used as a superconductor at room temperature and pressure. Generally, superconductors have other special features and it is not exhibited at room temperature and pressure, but then they are saying this LK99 can be used as a superconductor, that too at room temperature and pressure. Let us see furthermore details about this LK99. And if the claim that they are making, if it is going to be true, then surely it will revolutionize the world of electrical conductivity and technology. So it will surely revolutionize many more upcoming technologies. Okay. Next, what are superconductors? That we have to understand at basics level. Okay. So superconductors are materials that exhibit zero electrical resistance. This is the important term here. Zero electrical resistance, that too when cooled to extremely low temperatures. For other materials, only when they are cooled to extremely low temperatures, certain materials are going to exhibit this superconducting or superconductivity as its ability. Okay, so it means zero electrical resistance. Other than that, it also allows for the electrical conductivity without any loss of energy. So there won't be any loss of energy. So the key terms here are no loss of energy and zero electrical resistance. That is superconductors. Okay, next, examples for superconductors are lanthanum barium copper oxide, yttrium barium copper oxide. Other than that, we also have niobium tin as examples for superconductors. Okay, next, when was it discovered? When was superconductors discovered? In the year 1911, Kamerlingh Onnes, okay, he is a Dutch physicist, he is a Dutch man, Dutch physicist, he discovered that electrical resistance of mercury completely disappeared at temperatures few degrees above absolute zero. So he worked on mercury, that is one point. Other than that, what has he observed? He observed that the mercury exhibits zero electrical resistance at temperatures few degrees Celsius above absolute zero. So what is absolute zero here? Absolute zero is 0 Kelvin. Absolute zero temperature means, it means 0 Kelvin. In Celsius, if you have to say, then it is minus 273 degrees Celsius. Okay, minus 273 degrees Celsius is absolute zero, or it can be simply said as 0 Kelvin. Okay, so this phenomenon is called as superconductivity. Okay, so he worked on mercury, but then now the recent news is that L99 is going to work at room temperature itself. We saw, right? Only when the materials are taken to minus 273 degrees Celsius or near to that range, then materials will exhibit superconductivity. But then now they are claiming that even at room temperature and pressure, this can be achieved, and they have named it LK99. Next thing is, what are all the claims made by these scientists? First thing is, they are going to explore a special type of material called apatite. So what is this apatite? These are minerals with phosphate scaffold in tetrahedral or polyhedral motif. So this is how it will be looking. So this is the tetrahedral or pyramidal motif. Okay, tetrahedral or pyramidal motif of phosphate scaffolding. Okay, scaffold. Okay, that means phosphorus atom is surrounded by 4 oxygen atoms, is called as this model. Okay, the apatite model. So this is how it will be looking. There will be 4 oxygen atoms which surrounds the phosphorus atom. So the center one is the phosphorus atom, and then it will be connected to 4 oxygen atoms. Okay, so that type of materials or mineral is known as apatites. Okay, and the scientists started with lead apatite. They started their research with lead apatite, and slowly they substituted some of the lead atoms with copper atoms. So the resulting thing what they got is copper substituted lead apatite. Okay, copper substituted lead apatite. This is that LK99. So if there is a question asked in prelims that what is LK99 chemically, or what is LK99 and its constituents, then you have to say it is copper substituted lead apatite. Okay, so that would be the correct answer. Next is evidence of superconductivity on this LK99. So when they substituted 10% of copper instead of the lead, then LK99 exhibited the characteristics of superconductor. Okay, and this point is also important. It maintains superconductivity in the presence of external magnetic field. Actually, this kind of property is very typical to superconductors. So it maintains superconductivity even in the presence of external magnetic field. As we saw earlier, if the claim that they are making now is going to be true, then surely it is going to revolutionize the technological field, and because it will provide higher efficiency, energy efficiency, reduced power losses, and development of revolutionary technologies will happen in future. Okay, if these claims are true. Sorry. Yes. What are all the applications of? Just a minute. Yeah. What are all the applications of superconductors in general? Okay. First thing is energy transmission. This we already know that it is going to transmit electricity without losses, making them ideal for long distance power transmission. So energy transmission is one area where superconductors can be used. Next is magnetic resonance imaging, MRI imaging, that the medical field generally uses. Even there, superconducting magnets are used. Okay, so superconducting magnets are used in MRI missions to create strong and stable magnetic fields. This is one. Another thing is particle accelerator. We all know this famous Large Hadron Collider from which Higgs boson particle was created, the God's particle was created. Even there they use superconducting magnets. Next is electrical motors. Yes, superconducting materials can enhance the efficiency and power density of electrical motors and generators. Other than that, we also have another application, that is magnetic levitation trains. Okay, so superconducting magnets are used in this magnetic levitation train so that there won't be any friction while the train is running and there will be ease of movement. Okay, so it can also travel at very high speed. Next is quantum computing. Applications of superconductors in quantum mechanics or in quantum computing is being explored these days because superconductors are exhibiting quantum states. Okay, so these are all the applications of superconductors. So if at all there is a question about superconductors and about the recently discovered LK99, then you can use these applications in your answer writing. Okay, for your mains answer writing. The next topic for the day is demonstration rocket for agile cislunar operation, that is DRACO. Demonstration rocket for agile cislunar operation. What is this? It is an initiative jointly taken by NASA in collaboration with United States Defense Advanced Research Projects, that is DARPA. Okay, United States Defense Advanced Research Projects Agency, DARPA. And what are they seeking here? They are seeking for nuclear propulsion system for space activities. Okay, so far we are using conventional fuels for space activity, like if it is liquid fuel, then we go for hydrogen, liquefied hydrogen, and oxygen is used as oxidizer. But then now they are proposing nuclear propulsion systems for space-based activities. So this will potentially cut down the travel time of Mars by half. This is what they are aiming for. Okay, Next, this ambitious initiative is scheduled to be launched for, in late 2025 or early 2026. It will be launched. Okay. Next, Draco project is offering the prospect of shorter travel time. Yes, shorter travel time between celestial bodies and improved fuel efficiency, obviously. Next, a nuclear reactor that utilizes energy derived from fission of uranium atoms is going to be used. So in this particular session, we'll be talking in detail about the nuclear reaction, what is nuclear energy, how are these fission reaction and fusion reactions are going to take place, and what are all the different types of nuclear fuels we have, what is fissile material, what is fertile material, and all those distinctions we'll see. And at last, we'll also be discussing about uranium enrichment. Okay, since they're talking about uranium atoms which are going to be used for this nuclear reactor, we are going to see uranium enrichment process also. Okay, so yes, let us get into further more details of this thing. What are all the concerns raised here? Whenever nuclear fuel is used, okay, whenever a nuclear material is used, then there are certain concerns like safety concerns. First thing is, it can cause it has potential for accidents and malfunctions which could release radioactive material into space or back to Earth. So when they are going to employ nuclear reactors for propulsion in space-based systems, then there are chances for accidents and malfunction which will release radioactive materials, and surely it is going to cause severe environmental and health consequences if at all this happens. Okay. Next, launch risks. Okay. Generally, in rocket launches, we face launch risks like launch failure and explosion have happened previously. Okay. Even in India, we have faced this. Even in NASA and many other space agencies have faced this launch risk, and launch failure and explosion has happened. So, if it is going to be a nuclear fuel which is going to explode, then it is of a greater concern for environment as well as human health. Okay, so these concerns are there when we go for nuclear fuel, and how are they going to address this particular concern in this Draco program, that we have to understand. Okay. Next, comparing previous projects with this Draco program. Okay, is this the first time that they are exploring nuclear explosion, nuclear propulsion system in space-based activities? No, or even previously Orion and Nerva, these are the two projects where they explored nuclear powered propulsion system. But then it was a failure, it was not fully realized. But then the Draco is going to use nuclear fuel powered propulsion system, but then it is very different from the other two with respect to two features. First thing is fuel enrichment. Earlier in this project Nerva, they have used weapon grade uranium. So we have to understand what is weapon grade uranium. Okay, but then here in this Draco, they are going to use less enriched form of uranium. So if it is less enriched form of uranium, then it is going to minimize the risk associated with radioactive materials. That thing is there. How is this going to work? Those details we'll understand in the upcoming slides. Okay. Next is in-space activation. This is also very important. Only after the rocket reaches space, then the nuclear reactor will get activated. So until it is in the atmosphere, it will not get activated. Only after it reaches space, it is going to get activated. Until then, it will be dormant. Okay, so this is how they are going to overcome the concerns that we discussed in the previous slide. Okay, so it will mitigate the potential for radioactive accidents during launch or when it is in the earth, on the earth. Okay, so yes. Next thing is, as I said, we are going to understand in detail about what is nuclear force, what is nuclear energy, nuclear reaction, what are the types of nuclear reaction, and all those details, because at the end we have to understand what is uranium enrichment and other details, and then what are all the different types of nuclear reactions that we have. Okay, so yes, what is nuclear force? Nuclear force is the force that binds the protons and neutrons in nucleus together. Okay, so inside an atom you have nucleus. Okay, and inside nucleus you have neutron and proton. Okay, we all know that proton is positively charged, right? How are positively charged held together inside a nucleus? Okay, generally positively charged particles tend to repel each other, right? They tend to repel each other. But then here they are held together. That is because of the nuclear force. Okay, so this nuclear force is the one which is going to hold them together. Okay, the force can exist between protons and protons, two positively charged particle, neutron and proton, and also between neutron and neutron. So in this diagram you can see between proton and proton, between neutron and neutron, and then also between proton and neutron. That force is called as nuclear force, and this force is what holds the nucleus together, as we discussed. Okay, so we are going to disturb this force. Okay, when we disturb this force we get nuclear energy. Okay, so nuclear energy is a form of energy released from the nucleus, and nuclear energy can be produced in two different ways. First thing is nuclear fission, and second is nuclear fusion. What is fission? When nuclei of atoms split into several parts. Okay, the nucleus, if it is going to split into several other daughter nuclei, then that is nuclear fission. And nuclear fusion is nuclei fused together, smaller nuclei fusing together to form a bigger nuclei is called as fusion. Okay, in both these reactions, energy is released in enormous amount, and that we are going to harness for electricity production or for any other, for weapon purpose also they are using. Okay, next is the nuclear energy harnessed around the world today to produce electricity is through nuclear fission. This is a very important point. At present we are not employing nuclear fusion reaction for production of electricity, but then we are using nuclear fission reaction. Okay, so the technology to generate electricity from fusion reaction is still in R&D phase, and we are yet to exploit it. Okay, next, nuclear reactions. What is a nuclear reaction? How does a nuclear reaction happen? Okay, what is nuclear reaction in general? It is change in the identity or characteristic of atomic nucleus. So the atomic nucleus characteristic and identity is going to change. How it is going to change? Because of the bombardment of energetic particle. What are these energetic particles that we are talking about? They are alpha particle, gamma ray photon, neutron, proton, or a heavy ion. These are the energetic particles. If the nucleus is bombarded with these energetic particles, then nuclear reaction is sustained. Okay, the bombarding particle must have enough energy. This is also there because it must have that capability to disturb the nuclear force that we talked about. The force which is holding the nucleus together, that force has to be disturbed. So much of energy must be there in these bombarding particles. Okay, yes, generally neutron is used. In many reactions, neutron is used as a bombarding particle. Bombardment is nothing but hitting it. Next, nuclear fission reaction we'll understand in furthermore detail. Okay, nucleus of atom splits into two daughter nuclei. This is nuclear fission in general, and it can happen in two different ways. First thing is it can happen naturally, and second, it can also be simulated. When will it happen naturally? When it is spontaneously splitting by radioactive decay. So this will take a lot of time. Okay, this is going to happen in many other, it is happening in many nuclear materials. Okay, so it will happen spontaneously and it will split by radioactive decay, but this can also be simulated in lab by achieving necessary condition. What is the necessary condition here? As we saw earlier, it is bombarding with neutron, alpha particles and other things. Okay, next, the resulting fragments. What will be the results of this nuclear reaction? It will have a combined mass which is less than the original. Okay, so when you see the picture you will understand it better. See, you have a nucleus. Let us consider this to be the fissionable nucleus, the parent nuclei. Okay, parent. Upon bombardment with a neutron, it is going to split into two daughter nuclei. So you have two daughter nuclei. Daughter nuclei. I'm naming it DN. Okay. So what they are saying is the combined mass of these two daughter nuclei will be less than the mass of the parent nuclei. So a little amount of mass is lost somewhere, and that mass is what is going to get converted into energy. So this is the energy that we are getting from nuclear reaction. And further, how is the reaction sustained? From this first reaction, there will be release of neutrons. Okay, 3 neutrons will be released from this, and these 3 neutrons is going to sustain the reaction further because they will go and hit. Okay, here we are using incident neutron, right? So like these neutrons is going to hit other nucleus, and that is how the chain reaction is sustained. Okay, so now let us come back to the statements. So the resulting fragments have a combined mass which is less than the original. Now we have understood where that mass has lost. Okay, so the missing mass is usually converted into nuclear energy, and currently all commercial nuclear reactors are based on nuclear fission reaction, which we already saw. Okay, next, yeah, this is nuclear fission reaction. So you have nucleus, it is splitting open, and then daughter nuclei are formed, and then energy is produced. This energy is what we are going to harness for electricity production, and in that reaction also neutrons are formed, and these neutrons are going to sustain the reaction, further reactions. Okay, so that's why it's called chain reaction. It will go as a chain. Yeah. Next is nuclear fusion. Okay, first thing we saw is nuclear fission. This is nuclear fusion. Combining of two lighter nuclei into heavier one is called nuclear fusion. Generally, nuclear fusion in nature it occurs in stars. Okay, so it is the source of energy in sun and many other stars, but it takes considerable energy to force nuclei to fuse. Okay, so to force the nuclei to fuse, we need enormous amount of energy. See, the conditions needed for this process are extreme, like millions of degrees of temperature and millions of pascals of pressure is needed for combining the nuclei together to form a fusion reaction. This practically is not possible now, that is why we are not exploiting this much. But then here such, in fission reactions, such extreme conditions are not required. Okay. Yes. This is best example for fusion reaction, that is deuterium and tritium getting fused to form helium, and then neutron again is formed, and then energy is formed. This energy is harnessed. Okay. Yes. Next, we have to understand isotopes because we are going to talk in detail about uranium. Okay, what is uranium? And there are different isotopes of uranium. So, to understand isotopes, we have to know the basics of atomic number and atomic mass. What is atomic number and what is atomic mass? Atomic number is equal to the number of protons. So, the number of protons is atomic number, and atomic mass is the sum of proton and neutron. Okay, so if it is atomic number, then it is proton alone, and if it is atomic mass, then it is proton and neutron together. So whenever we write an element, we write atomic number here like 92, 235 like this. Uranium 92, 235, which means what we are writing here is atomic number and what we are writing here is atomic mass. This is how we write. Okay, then what is isotopes here? We said we have different isotopes of uranium. What is isotope? Are atoms with same number of proton but have different number of neutrons. Okay, so there will be same number of proton. Say if there is another isotope of uranium, it will be having same number of proton, but then the number of neutron is going to change. This includes proton and neutron, right? Here it includes proton plus neutron. So here it will be changing. So 238. In next slide, I'll show you the picture so that you'll understand it better. So in other words, isotopes are elements with same atomic number and different mass number. That way also we can say, right? So same number of proton but have different number of neutrons. This is one way of describing what is isotope. And other way is elements with same atomic number but different mass number. Okay, this number is the mass number, atomic mass number. Okay, so we'll understand that with an example. There are many types of uranium. Okay, uranium 235 and then uranium 238. Here 92 is the atomic number or the number of protons. See, number of proton, and here the number of neutrons is 143. So 92 plus 143 is 235, and here again the neutron numbers is 146. So 146 plus 92 is 238. So that is how they are different. So isotopes of any particular element contain same number of proton but different number of neutrons. So these are isotopes. These basics are important because questions from basics are also asked. Next, we have to understand what is fissile and what is fertile. Okay, there are two types of materials when it comes to nuclear energy. One is fissile material and another is fertile material. We have to understand. So fissile materials are the one that can sustain chain reaction. We saw chain reaction, right? Upon bombardment with a neutron, the chain reaction is sustained. So those material which can sustain a chain reaction are called as fissile material, and examples for that is uranium 235, 233 and then plutonium 239. These are also called as driver. Okay, so fissile material are also called as drivers. These examples are very important. That is how that is why it has been highlighted. Next is, it drives the chain reaction to produce energy while simultaneously transmuting the fertile material into fissile material. So for this we need to understand what is fertile material first. Okay, then only we can understand this particular statement. So what are fertile material? Fertile meaning that it can transmute into fissile material or fissile radioisotope, but itself cannot keep the chain reaction going. So it cannot sustain the chain reaction, but then upon bombardment by a neutron, it will get converted into a fissile material. Okay, so if it is fertile material, if it is fissile material, then chain reaction will happen. But if it is fertile material, chain reaction will not happen. It will get converted into a fissile material. And in the next step only, this fissile material, when bombarded with a neutron, it will give rise to a chain reaction. Okay, so this is the link between what is fissile material and what is fertile material. Best example for fertile material is thorium and uranium 238. Already we saw, right? There are two isotopes, naturally occurring isotopes of uranium, that they are, they are uranium 238 and uranium 235. Okay, naturally occurring, these two are. Next, thorium, again a fertile material. Next, we have to understand examples of fissile and fertile material in detail. Only with these materials we will be dealing much here in nuclear reactors. First thing is uranium 233, 235 and 238. These are the three isotopes of uranium which is widely used in nuclear reactors. Of these, 233 and 235 are fissile material, which means they can sustain the chain reaction. But 238 is a fertile material, which means upon bombardment by a neutron, it will get converted into a fissile material, but itself cannot sustain a chain reaction. Okay. Next, upon bombardment with neutron, uranium 235 and 233 break down to produce heat and neutrons, as well as two lighter nuclei, as we saw in the reaction, the nuclear fission reaction. But uranium 238 will get converted into plutonium 239. Okay, so see the reaction. If it is uranium 233 or uranium 235, then chain reaction happens. When uranium 238 is bombarded with a neutron, then plutonium 239 is obtained. Okay, here plutonium 239 is a fissile material. It can be used in the next stage. Okay, in the next stage it can be used as a fissile material. Okay, so here plutonium 239, okay, which is a fissile substance. Next, you have thorium 232, which is a fertile element. It changes into uranium 233. Okay, so uranium 233 is a fissile material, as we saw earlier, but it is not naturally occurring. Only in this reaction you will get uranium 233 as output. Okay, so when thorium is bombarded with a neutron, it will convert into uranium 233, which is fissile material, whereas the base material, that is thorium, is a fertile material. So when we summarize this, yes, uranium 235 uranium 238 and uranium 233. Of this is a fissile material which is naturally occurring. Okay, so chain reaction happens in this. Uranium 238 is converted into plutonium 239 in the first step. But this plutonium 239 is a fissile material, which means in the next step it will sustain chain reaction. Okay. Next, uranium 233 is not naturally occurring, whereas these two are naturally occurring. So uranium 233 is obtained from thorium 232. So from thorium 232 you get uranium 233, which will then sustain chain reaction. So these three are fissile material, whereas these two are fertile material. So this is how we have to understand it. Okay, this is the overall reaction which you must have to understand. Okay, we'll understand about India's nuclear program in some other session in detail. There again I'll be discussing all these things. Okay, next thing is uranium enrichment. Like we saw in the first in the introductory slide, we saw about uranium enrichment, because in this DRACO program they are going to use nuclear reactor with uranium which is not enriched to higher levels but then enriched to lower levels. So what is this two types of enrichment, high enrichment and low enrichment, and what is this enrichment basically? All those details we must have to know. So enrichment is an artificial process in which the percentage of uranium 235 is enhanced. So what are they going to enhance here? Uranium 235's percentage is going to get enhanced. Why are they focusing on uranium 235? Because it is the fissile material, first thing. Another thing is, it is a naturally occurring ore, a mineral. Okay, so naturally occurring uranium is comprised of two isotopes. One is uranium 238 and another is uranium 235. But then see this percentage. Naturally occurring uranium consists 99.3% of uranium 238, which is not fissile, which is fertile, like we saw in the previous slide. So it is not fissile, which is fertile. But then the naturally occurring uranium has just 0.7% of uranium 235, which is fissile. But then the percentage here is very less. This has to be enhanced, and this enhancement process is called as enrichment process, uranium enrichment. Okay, so the enrichment process, the percentage of fissile isotope is increased by many methods like centrifuges, gaseous diffusers, modular laser isotope separators. These are the methods which we are going to use for enrichment. We'll understand that. So these are the process that is used. Gas diffusion is there, gas centrifuging is there. Next, molecular laser isotope separation. These processes are used for enrichment process. Okay. Next, there are two categories of enrichment, like we saw, low enriched and high enriched. So what is the difference? Low enriched means the percentage of uranium 235 is equal to or less than 20%. If it is less than or equal to 20%, then it is called as low enriched uranium, and it is used for peaceful processes like fuel for nuclear reactor to produce electricity. Okay, so for peaceful processes they are going to use low enriched uranium, and the best example for this is in India, in Jaitapur nuclear reactor they are using just 5% enriched uranium as fuel. Okay, so just 5% is also enough for using it for electricity production, okay, for peaceful purposes. Next, you have high enriched uranium, which means they are also called as weapon grade uranium because they are enriched to 90% and above. Okay, so the percentage of uranium 235 can go beyond 90%. That is called as high enriched uranium, and it is used for conducting nuclear tests and also for configuring nuclear weapons. That is why it is also called weapon grade uranium. Okay, so a question based on this was asked in 2023 prelims examination, that we will see. Consider the following statements. Statement 1. India, despite having uranium deposits, depends on coal for most of its electricity production. Yeah, that is a true statement. Okay, though we have uranium deposits in monazite sand of coastal areas, especially in Kerala, we are depending more on coal as fuel for electricity production. That is a correct statement. Statement 2. Uranium enriched to the extent of at least, this word is very important here, at least 60% is required for the production of electricity. Just in the previous slide we saw less than or equal to 20% is also enough for production of electricity. That is for peaceful purposes. Electricity production is a peaceful purpose of using nuclear fuels, right? So less than or equal to 20% is enough for producing electricity. At least 60% is required is what they are saying. So this statement is a wrong statement. So the answer for this would be statement 1 is correct and statement 2 is incorrect. Okay, so this was 2023, the previous year, I mean this year's prelims question. Okay. Yes, with this we are coming to end of this nuclear reaction. This Draco news is done here. Okay. Next news is conjunctivitis. What is conjunctivitis? Conjunctivitis is an infection which is happening in the conjunctiva of eye. What is conjunctiva? Conjunctiva is a thin membrane that covers the white part of the eye and lines the inner eyelid is called as conjunctiva. When there is infection in that conjunctiva, that is called as conjunctivitis. Okay. In monsoon season, due to high humidity and rainfall, there will be favorable condition for this infection to spread among people. So that is why we are facing conjunctivitis case in many parts of our country. Okay. So it is also called as pink eye. Okay. Next, it causes redness, itching, discharge and pain in the affected eye. So all this happens when you are affected with conjunctivitis. Next thing is, so yeah, this is conjunctivitis. This portion, this part is called as conjunctiva. So this is the black part of the eye, the center part of the eye. In that you have cornea, pupil, iris, lens and other things. And then the eyelid and the white part is covered with a membrane called conjunctiva. Okay, a thin layer called conjunctiva. Okay, if that is infected, you will face this redness and itchiness and all in your eyes. So there will be inflammation also. Next, there are 3 causative agents for this. One is virus, another is bacteria, and the third one is allergens. If it is caused by viral and bacterial infection, then it can spread through direct contact with that person with contaminated hand or surfaces. But then if it is through allergens, then it is not contagious. So viral and bacterial conjunctivitis are contagious, whereas the allergic conjunctivitis is not contagious. And how can we prevent it? Obviously, we must have to wash our hands frequently, avoid touching or rubbing eyes, not sharing personal items with others,